Good afternoon, everybody. Let's start out with some graphical evidence on the nature of the solutions to this absolute value square root equation. Now, this is just the real number line, so we'll locate 0 here in the middle. Now, just very familiar transformations. If you come over to minus 30, which is where this absolute value would be equal to 0, so this would be minus 30 right here. The coordinate would be minus 30, 0. And of course, the very familiar shape of the absolute value graph. You got something like this. Okay, not attempting to do any kind of scaling on the vertical axis. Now, on the horizontal axis or the vertical axis, which isn't drawn. Now, notice right here, this would be 0 at the point, and I'll exaggerate this just a little bit since I have fat fingers here. That would be what, minus 2 or 33? Yeah, minus 2 or 33, a small number. Well, a big negative number actually, right? But the point is it's on this side of the of 0, so it's negative. 2 over 30, minus 2 over 33 would make this part 0, okay? So the minus sign does a reflection about the this vertical line right here. It's not part of the graph, okay? It's a reflection of the square root function. And no, it does not go down. I'm not going to do it, folks. It keeps going up. I just got excited right there. But you can see there's going to be two solutions, okay? The square root function grows slowly, but it keeps increasing, all right? I can actually be professional and erase that. I know how to do that. Wait, let's see. Eraser. Oh, I erased the whole thing. Okay, so let's just go like this and try to keep going up, okay? Horrible picture, folks, but that's the graph of the square root function reflected about this vertical line located at x equals minus 2 over 33. All right, now the absolute value has a square root, a squaring interpretation. In other words, a lot of you are used to seeing the piecewise, but the absolute value of A also is, in my opinion, a little more continuously defined this way, the square root of A squared. And that just comes from the Euclidean norm in one variable, basically. It's something very, very believable. They teach that piecewise definition, which I think is kind of clumsy. This is the definition of absolute value, in my opinion. I guess the piecewise has some value, but anyway. So that's what I did right here, folks, going from here to here, okay? Now, we have another nice little thing going on here. Square root function is 1 to 1. Now, what do we mean by 1 to 1? If you have a function is 1 to 1, if you have f at x sub 1 equals to f at x sub 2, if that always implies, and this is for all such ordered pairs or values in the domain, that implies, and actually, well, I won't say if and only if I guess, but that implies that x1 equals to x2. So see, what I like about what I'm showing you today is I'm not having to square anything. I'm just working from the definition of absolute, of the square root function, okay? It's 1 to 1, that's what this means. So that means we can simply remove the square root function and equate the two input arguments. It's kind of nice. No squaring required. I don't see this taught that much. Everybody's just fond of squaring and checking to see if you have extraneous solutions, blah, blah, blah. It's kind of tedious and mindless, in my opinion. So now, when we do them, we end up with this quadratic, okay? Now you're saying, well, that looks like fun. You got a very large constant. But notice, folks, the prime factorization of 902 is very easy to calculate. We know that 2 is certainly a divisor of 902, right? Now notice this is divisible by 11, folks. If you look at 2 minus 0, this is the alternating test for divisibility by 11. If you sum all that up, and the sum of this is 11, folks. Sorry, I forgot to write the plus signs in between there. But that's 11. And that, if you got 11 or any multiple of 11, that would indicate this number is divisible by 11. And y'all, this should be plus here. Well, I already had a minus sign. I could have gotten away without that. Okay. Okay. But anyway, what we end up getting here is this is 2 times 11. Now, this would require a little bit of work manually, but you get 41. Okay. 2 times 11 times 41 is the prime factorization. Okay. Now, notice that if this is going to factor, it has to admit this form right here. Now, folks, what are we doing here? We are looking for two factors that sum up to 93, or two divisors, two integers that sum up to 93, and whose product is this number. You see, but this it's right in our face. You can see that x plus 11, put x plus 11 right here. Now what's left up here, if you put 11 right here, 2 times 41 is 82. You see how nice that is? That's why prime factorization is so handy sometimes. It gives you a way to see the divisors. There's actually 8 total divisors here. There's 8 total divisors. If you look at the exponents and you increment them, and each of these has an exponent of 1. Okay, and if you increment those exponents and multiply them, you get 8 divisors. But these are the 2 divisors, and just manifestly, it works without even having to do anything. So the prime factorization is a big deal right here. So what we get right here quickly is x equals to negative 11 or negative 82. And no need to check. Absolutely no need to check. Everything we did was legitimate. We didn't have to square anything. And we got our answer of minus 11 and minus 82 are the 2 integers. Okay, folks, that is all. I thought it was cool. So let me know what you thought about this technique that does not involve squaring.